I love meteorology and atmospheric science. It is a cool science that we all deal with. I can show you how to understand the weather, the atmosphere, environmental science, climate, all of that. That's today on High Peak Education.
We just have the last bit of the convective storm matrix to finish up, namely K through P. So these are the hodographs that either are a half circle in terms of the hodograph shape, or they are quarter circle in terms of the hodograph shape. And it turns out they either go up to 5 kilometers in experiments K, L, and M, or they go up to 2.5 kilometers in N, O, and P. The wind shear varies. So we go 20, 30, 45 meters per second, then 10, 20, 30 for the other experiments. So then we're going to investigate K1, L1, and L3. Now K1, so because red wind direction rotates, could be supercell, but remember K1, that is locate, and 20 meters per second wind shear is not really significant. So let's start to investigate this. So I'm not seeing a lot of precipitation. The cold pools are pretty thin and pretty insignificant. I'm not seeing a very rounded structure, and I'm not seeing it rotate much. I mean, like maybe a little just because of the hodograph. Let's go ahead and go to 4 kilometers. So it does have some reforming updrafts in terms of those red splotches, but it's not like extremely wide or anything. Let's look at this three-dimensionally. So let's look from the top down first in terms of the cloud field. So there's an updraft, there's a reformed updraft, there is a cold pool. The cold pool is not very significant. This thing's not propagating very much. I mean, it's got the help from the rotating direction on the hodograph, but it doesn't have extremely much shear. Looking from the side view, it looks to me that you've got this convective tower goes up and rains straight down. Another convective tower right next to it comes up straight down, and then very little propagation, if at all. It says a weak multi-cell system. So I would generally agree with that. You originally said ordinary. It was hard to say, so I would say multi-cell. That's because rotating wind direction with height makes good use of the shear, but such weak K and it's just going to give us weak updrafts. So I would call this multi-cell, but it turns out it's just very weak because there are multiple updrafts, but there's no mesoscale vortex. To go on to L1. So the main thing we change is we keep the shape of the hodograph exactly the same, but we increase the magnitude of the wind shear to 30 meters per second. So let's just look at 0 to 4 kilometers. So it looks like this thing is rotating from above. So the precipitation field has some rotation in it. There is a cold pool that does propagate along with this thing out front of it. So because of having that extra wind shear, it's looking more like a supercell. Let's look at the 4 kilometer level. Yeah, this thing has a little bit of rotation with it. Okay, you can kind of see it there in the wind field. You can kind of see it in there in the precipitation field. The cold pool, even at mid levels, is there. Let's look at the three-dimensional version. Okay, let's look from the top view down from the upper clouds. So there's an updraft. Looks like the updraft does rotate. It looks like there's another updraft, but the one on the north end is not going to be as much favored. So we talked about this before with the Coriolis force. The right movers in the northern hemisphere tend to be favored if these are supercells.
So I kind of mentioned this idea of splitting supercells a couple times in these videos. I wanted to take a quick second and interject what that really looks like. The supercells actually split from one single rotating cell. There's an enormous amount of wind shear, and as that mesoscale vortex rotates and we have some precipitation in the center, we actually get that the two split because the vorticity, that's the spin, splits into two different pieces. Now, I'm not going to go into all the dynamics of this, but we do observe this many times in the atmosphere and on radar. We can see that the supercell motion is here in green, whereas the 0 to 6 kilometer mean wind is in red. And you notice that there's one supercell that tends to move further north and west, and then the other one tends to move more south and east. A lot of times, depending upon the wind shear profile, one of these two storms tends to be favored. Now, do you see that this one rotates in terms of the hodograph? We get the rotation, which is favoring a left mover. Okay, so in this case, the left moving storm tends to be more favored. In the radar animation I'm about to show, you'll see that the right mover tends to be favored more often because of the wind shear profile in the United States and because of the Coriolis force, that is the cyclonic rotation in the northern hemisphere. So here's a good example of a left mover and a right mover in terms of how these storms actually move. This is an example from Texas from April 2020. Notice the one storm was moving kind of more north and east, the other was moving more south and east. And that's because these left mover and the right mover, did you see how they split? So this is what you expect to see on radar. You see that these storms split, and the splitting of the storms is indicative that these indeed are supercells. And so this is what you can look for. And it turns out when you see that going on in the atmosphere, you can usually expect that we have significant rotation of supercells. Could say more about this. Maybe I'll make another video. Let me know in the comments if you want to hear more about the dynamics of this. But let's get back to the rest of today's content.
Looking from the side, you can see these cells do split and separate. But I would not call this multicellular because of the rotation, and they haven't merged at all, or at least not yet. So I'm leaning towards supercells. So they say it's a weak, shallow, cyclonic, right-moving supercell. So I would agree with that. Enough shear and direction rotation. It's weak only because we don't have much cape to work with, but I would definitely favor supercells. All right, let's look at L3. So the main difference with the L3 is we've got high cape and moist conditions at low levels, keeping the shear profile and the changing wind direction the same as L1. So it looks like we're getting some splitting. We're getting a right mover and a left mover, and it looks like we do have some cold pools. Now these cold pools do have some curvature to them. They're displaced out front of the precipitation. And if I look at each of these wind fields, it looks like there's possibly some rotation. Now there's a little bit of elongation because I think that not only do we have significant cape, we do have significant wind shear. So we are pushing the rain down over. Okay, so it's a similar story to what we saw before. This looks a little more congealed and coherent at 4 kilometers here than 0.4 kilometers, which was 400 meters. Notice this kind of has that signature of being a single distinct cell. Notice, again, I'm mostly focused on the right mover. The right mover tends to be favored in the northern hemisphere. So I'm looking on the south side of these splitting cells. Okay, so looking from above, it looks like the cloud field does have some rotation. It has some circular nature to it, especially on the lower right side. And then on the top side, because the rotation for the left mover on the north end is not as favored as the right mover, I would say the northern left mover evolves into a multicellular complex sooner because there's just less rotation. It's not staying a supercell nearly as long. So I think we do want to classify this situation for sure as a supercell. It's just that later it evolves into a multicell, but it's just that a lot of convection when you go into the late afternoon and into the evening tends to congeal anyway. Supercells are much more common to evolve out of the blue, like out of clear air, whereas multicellular systems and then even squall lines and MCSs are going to be when the cold pools tend to merge and then the convection tends to be more slabular in nature. With that, I'm going to say this should be a supercell with good shear and cape. And then looking at the summary, like it says, cyclonic right-moving supercell evolving into a multicellular system. Yeah, I would definitely classify this as a supercell. It's really the supercell that dominates on the southern end, that is the right mover. And then finally P3. So P3, we're going to have the same shape of the hodograph as we just had in the O simulations. We're going to have more wind shear, and this time we're going to crank it up to high cape. So this is kind of like a disorganized mess. This has quite a large convective purview, and there's quite a few updrafts here. These do look distinct somewhat at first, but I would say, look at the cold pools, that yellow, that the cold pools tend to congeal pretty early on, although they stay somewhat distinct. Let's look at 4 kilometers. Again, on the lower right, it definitely does look a little bit like a supercell, a little bit. It doesn't tend to show that much rotation because the wind shear only goes up to 2.5 kilometers. But it does have some distinctness to it. Okay, so only when it breaks free right there, when the cloud breaks free from the rest of the cold pools in the line, when it starts to get further south and east, it looks to me like it looks a little bit more like a supercell, but it quickly evolves into a multi-cell complex. As you can see, there's multiple cells. The cold pools have sort of merged. They're like influencing one another. If I look at the side view, again, you can see bam, 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 bam. Look at all those updrafts. And that's because we have a lot of heat and a lot of moisture at low levels. But we just limited on the wind shear to get really significant supercells, classic supercells. So they say strong supercell / multicellular line evolving into a bow echo. If I had to make a call here, I would label this multicell because there's supercells along the line, but they quickly merge. So I would call that multicell. Part of the reason I think each of the summaries on Comet has like a bit of a description that goes with it, because 3 categories, ordinary, multicell, and supercell, are not necessarily sufficient for a full description when laying this all out. But I think there's just too many updrafts and too much merging of the cold pools here to think of this as like supercells. It's really like a line, and a line with multiple updrafts, even though there's some rotation. So I would call it a multicellular line with some supercell characteristics. That's what I would say. Let's go to number 4. It says, what is the impact of keeping CAPE roughly the same, but decreasing the low-level relative humidity? In other words, you increase the height of the LCL in environments conducive to supercells. So in other words, compare cases I3 and I4, and H3 and H4, M3 and M4. Let's think about what happens when we essentially change the relative humidity. Let's do it in the order of M, then H, then I. So now let's go to 4 kilometers and let's go to M4. So if you cut off that access to low-level moisture, let's see what happens. So certainly the supercell, if it is a supercell, looks a lot more weak. Let's see what they said as far as summary. This is a cyclonic, right-moving supercell evolving into a multicellular system. Yeah, so I would agree with that. The thing is, though, like, let's look at the low levels for a second. 0.4 kilometer. It definitely looks like a supercell, but it kind of congeals quickly because you just don't have enough moisture to kind of keep it, the updraft, separate, because you got a lot of dry air entrainment. Let's now go to the H simulations. Now, by the way, I'm going to predict that in advance, the I simulations should be the worst offender of having that upper level dry air, because you have so much shear that you're going to entrain a lot of dry air, especially like 3 to 9 kilometers or so. So this is a very long Hodograph, 45 meters per second vertical wind shear, rotating the direction at the bottom. It does look like a supercell to me. It's just that, like, what's happening with this one is we are pushing the precipitation out front, but the updraft is not nearly as ferocious as in H3, but it does look like a supercell. And let's look at the summary. Dominant cyclonic right-moving supercell. I would say it's not as significant of reflectivity and not as significant of an updraft. Because remember back to even your thermo classes, right? Low-level moisture, one of the things it does is it doesn't just provide fuel for the storm, for the actual hydrometeors. We get the release of latent heat as air parcels rise and then they condense. So when they condense, that latent heat release increases buoyancy and makes the updraft stronger. All right, let us go to now the I4 simulation. So this is a very long Hodograph. Yeah, now look at this. We can kind of tell, sure, it's a supercell, but it's really spread out and doesn't have as much moisture as the I3 simulation. Okay, but it still looks like a supercell. Strong, dominant, cyclonic, right-moving supercell. Yeah, but the idea is that, again, just not as significant of an updraft and not as strong of a supercell. So all of these situations still produce supercells with the low level moisture in place, but upper level moisture lacking. The main difference is that the strength of the updrafts is less in the 4 cases compared to the 3 cases. This is due to, and it's mostly 2 things that we've talked about before: less latent heat release due to lacking moisture to increase updraft buoyancy, less moisture in the 3 to 9 kilometer levels allows the vertical wind shear to entrain larger amounts of dry air, making the supercells shorter lived and having less strength. What is the impact of the depth of the shear layer on the storm structure and evolution? Hint, compare cases P3, L3, G3, in which the 30 meters per second of the Hodograph length is distributed over either 2.5, 5.0, or 7.5 kilometers depth. So generally, this is how the wisdom goes. We often say the longer the Hodograph, in other words, the higher height the Hodograph goes up to. Generally, that is more conducive of supercells, and it is going to give you more rotation. So let's look at P3 first. So we've got 30 meters per second wind shear over the lowest 2.5 kilometers. So we do have some level of supercells, but if you recall, this is kind of more like a multicell line because it's only over the lowest 2.5 kilometers. And then the summary is strong supercell multicell line evolves into bow echo. Then let's look at L3. Now L3 is the exact same shape, but it's going to be a circle which goes up to 5 kilometers. So since the wind shear is distributed over a much larger depth of the atmosphere, even though it's the same wind shear, just because we stretch it out to a higher height, we do get a much more distinct supercell. So the supercells are much more discrete. They're not so slabular. So G3 is still 30 kilometers of vertical wind shear. We're going to now stretch it out all the way to 7.5 kilometers. So we have a supercell. Now, by the way, this is not a perfect apples to apples comparison because we have a rotation, but then we have a straight line Hodograph. So the rotation of P3 in the lower levels then has the straight Hodograph after that. So when you compare P3 to L3, keeping the rotation of the wind direction going and stretching out the Hodograph to higher height gets more distinct cells. P3 to G3 just says, let's add on more wind shear depth. You are getting more distinct cells, but it turns out because the rotation is not through as much of the depth of the atmosphere as the 0 to 5, like in L3, then it's not as round. The most direct comparisons we can make are P3 to L3 and P3 to G3. We can say the increase in depth of the rotating wind direction Hodograph allows for more ingested storm relative helicity, and the supercell is more round and distinct. Then let's have a look at P3 compared to G3. So the increase in depth of the vertical wind shear makes the supercell more distinct, separates the storm from its neighbor by displacing the precipitation downstream, downwind to the east. So we get a longer lived, more significant supercell. It is slightly more round. There's no more storm relative helicity ingested when we compare P3 to G3. We just have a longer Hodograph. So we're leaning the storm over, pushing the precipitation downwind, downstream, more so over a more significant depth when we do G3.